Hello everyone, my name is Shahin Khoddam. In the next 10 to 15 minutes I'm going to present a model to describe high pressure torsion processing of a cylindrical segment sample. This work has been done in collaboration with Professor Peter Hodgson from Institute for Frontier Materials, Deakin University, Australia, and Professor Mohammad Habib Parsa from Tehran University. Author's affiliation: the corresponding author, I'm presenting this work. High pressure torsion is a very promising technique for creating nanostructured material. Most of the existing work are experimental. There are very few existing analytical frameworks to describe the process and to predict and to improve the process. These techniques, we refer to them as traditional techniques. And as you can see, the setup for the process includes a die, sample, upper punch, lower punch. One punch is stationary, the other punch is rotating at an angular velocity. And the cylindrical sample is quite axisymmetric. It has the axis of rotation coincident with the z-axis. So that's what the traditional analytical technique is about. The immediate conclusion from these assumptions are material velocity field can be described by one single velocity component, the tangential velocity, because the process is a zero shape change process. Height doesn't change, the diameter doesn't change, and the only deformation is due to shearing stress from tangential velocity. And that velocity is zero at the center. It linearly increases to its maximum at the periphery, and again there's a linear distribution from top to the bottom. That maximum velocity vanishes to zero here in a linear sense. And if we translate these assumptions into definition of strain rate components, we notice that the only non-zero strain rate component is the shearing z theta. From here we work out the effective strain rate, and that the model tells us there shouldn't be any strain rate along the center line. And if we work out the effective strain rate by integrating through a deformation streamline, again there shouldn't be any deformation along the center line when the R is zero. When we look at the experimental observation, it doesn't comply with the predictions from this mathematical model. And as we repeat the process, the material work hardening, grain refinement, they tend to become rather uniform, and this is by no way the linear work hardening predictions from the existing model. So let's have a totally different view angle toward the problem, something more realistic. To do that, we consider the sample to be a cylindrical segment rather than a perfect cylinder, and this cylindrical segment let us to account for the inaccuracies in the sample and the misalignments in the setup. So here we are showing exaggerated views from both cylindrical segment and the setup. That is for ease of understanding and for better illustration. This is an important figure. Here we notice that the height of the sample is not uniform. It starts from its minimum at the left hand side to its maximum at the right hand side. There's a height runout, and a very important parameter here is rho. Rho is radius of rotation. If CC prime is instantaneous center of rotation for material, Z axis is coordinate system axis. They are not necessarily coincident. And here we have a typical height for the sample described at some certain radius and some certain height. So let's develop on this geometry. We can work out the typical height for a given radius and given time frame as a harmonic function. And to show you snapshots of this transient geometry description, 4 time frames have been considered here, and in all these figures the coordinate systems are in the same position, but the sample is rotating. The intersection between coordinate system and sample gives us a quadrilateral shape, and this quadrilateral shape is not uniform. As the sample rotates, the quadrilateral changes in shape. Let's call this quadrilateral the representative window. So that always is in the ZR plane, but its shape changes. So the minimum maximum of h are represented to the time equal to 0. show you an animation of top surface for the cylindrical segment due to rotation. Here we see the top surface as a line, and as the sample rotates, that's what happens to the top surface at the cross section. Now we have described the height for typical point in the sample. One very important finding here is the area of the representative sample. If we work out this integral, surprisingly we find out that the area doesn't depend on time. It's a constant area. Average height is constant, radius is constant, so no matter what time frame is under consideration, the area for representative window is the same. We are going to make an important conclusion from this. We assume that within the representative window, material flow is described by two velocity components only, u dot and v dot. And since this area doesn't change, we can conclude that divergence of material velocity field inside the representative window is zero. In mathematical terms, that's what the divergence when divergence vanishes. And since we had the description of h with respect to time, we can simply find its rate, and then we find out the first velocity component in this representative window, and also we can work out the displacement. This is the axial displacement. If we remember cross section of representative window and the location of CC prime, which is the instantaneous center of rotation, we can divide the representative window into two parts, A1, A2, in the left hand side, right hand side. A1 is the portion of representative window where the material flow is inward, normal to the plane, and A2 is the right hand side portion of the representative window when the material flow in the tangential direction is outward. So these two should be equal. That's due to the volume constancy or area constancy. And in mathematical terms, we can write these integrals, carrying out this integration and doing a little bit of simplification. We come up with an important relationship. That's the distance between instantaneous center of rotation CC prime and the z-axis. So now we know how this thing changes with time. It's not necessarily zero. Only at certain time frame that runout is zero, but for the rest of times this grows and shrinks, but it is always is there. So delta is height runout, r is radius of the sample, and depending what time frame it is, we can work out the distance between these instantaneous center of rotation. And from here we can establish the tangential velocity by considering rho and the distance between instantaneous center of rotation and geometrical axis. So plus minus signs are corresponding to A1 and A2 respectively. So this velocity field is now fully described and it complies with the boundary conditions. We see that this is zero at the bottom surface of the sample and it fulfills all other boundary conditions. Important conclusions we can make here is currently the existing high pressure torsion models are not adequate to describe the experimental observation. A cylindrical segment geometry was used here to account for inaccuracies in the sample and misalignment in the tools. We propose a kinematically admissible velocity field which fully explains the non-zero flow of material in across the whole sample. Since we have the description of velocity field, one can use this to develop for accelerated components and effective strains, and that should be enough to describe the structural changes within the non-ideal sample. Thank you for your time. That brings my presentation to its end, and I'm happy to take any question. Thank you.